di short lecture. Dan juga I would like to welcome and thank you to Dr. Tang Wali and Dr. Hilim for their time to able to present their excellent work to all of us. I already give a link for their publication in Nature Communication, ya. And Pak Kapu sudah ada belum ya? Maybe Pak Sulaiman. Oh, he's not here yet. So I think first I will introduce our speaker. First speaker is Dr. Tang Wali. He will present his talk entitled Sea Level Change in Singapore and Southeast Asia, Implication from Past to Future. Dr. Tang Wali is a senior research fellow at the Earth Observatory of Singapore, Nanyang Technology University. And he obtained his PhD in geophysics from the University of Hong Kong and received his bachelor in geophysics from China University. And Dr. Lee's research interests include interaction of ice, ocean, and solid earth and their lasting impact on the Earth system, with a specific focus on modeling the glacial isostatic adjustment process with 3D model and associated sea level or ice evolution, vertical land movement, gravity field change during the last glacial cycle. And his research contribute to the better understanding of Earth geological structure and deglaciation history, which help to consent estimate of the future sea level change and understand the response of ice to climate change. Dr. Lee is also interested in interdisciplinary studies exploring sea level change impact and applications. And the second speaker is Dr. Hilim Kim, Associate Professor at Asian School of the Environment of Nanyang Technology University, Singapore. Her presentation today entitled Prehistoric Human Migration Between Sundaland and South Asia was driven by sea level rise. And Dr. Hilim Kim, specialist in population genomics, which studies genetic variation between population to understand their demographic history. And she received PhD training in population genetics from the Graduate University for Advanced Studies in Japan, and continue her postdoctoral research at Pennsylvania State University. And currently she is leading Genome Asia 100K project, a massive research initiative aimed at generating and analyzing population genome dataset from diverse ethnicities in Asia, and to refer the genetic diversity and population history of ASEAN populations. I think that's all for now for the introduction. And I will give floor to Gino to lead this seminar, and also for for moderator. Gino is here?
Yeah, sure. Yeah.
Okay,
yeah.
now
okay, thank you, Yuda. No, thank you for the nice introduction as well. I have not much to add to that. So yeah, so I think let's enjoy this seminar. I forgot who's starting.
Dr. Tang Huang Lee, the first.
Okay.
Yeah.
Then I give the floor to you. I'm looking forward.
I will share my slides first. Let me be slow. Do you all see my screen?
Yeah, I think it's
Okay, I will make it full screen. Is it full screen now?
yeah.
Okay, great. So morning, everyone. Very honored to be here to give the PRIMA talk. Thanks for Yoda and Gilo for the organization of this series. And my talk is about the sea level change in Singapore and Southeast Asia, the implications from past to future. So on the left panel, you see my structure of this lecture. First, I will give a very brief introduction of the EOS and also myself, and followed by the sea level processes that drive sea level change and past, present, and future sea levels. Finally, a very brief summary of my talk. So as you all may know, the EOS, the Earth Observatory of Singapore, is a government institute, funded research institute, and mainly conducts research on the earthquakes, volcanic eruptions, tsunami, and climate change in and around Southeast Asia. And here shows you a map of the hazards threatening our region. You may know the 2004, the Great Sumatra earthquakes, after which the EOS was founded. The government mainly wanted to have a better understanding and knowledge of the hazards in and around Southeast Asia. So that's the main task for EOS. We have the seismic and tsunami hazards, team, volcanic hazards, typhoon and cyclone hazards, as well as the sea level rise hazard, which is the main target of our research group, led by Prof. Benjamin Horton, the director of EOS. So for myself, as Yoda have introduced me before, so no need to further demonstrate. I will go to my slides directly. So here shows the schematic modified after IPCC AR5, which shows the sea level driving processes. As you can see here, the sea level is mainly driven by a variety of global, regional, and local processes that vary spatially and temporally, such as the atmosphere and ocean dynamics, thermal expansion, the tectonics, and the ice sheet and glacial isostatic adjustment, which is the interaction between the ice sheet from the Earth and the ocean. So I will follow from global, local to regional to show several representative processes. So here shows you the global driving processes that mainly emphasize the global response to an increase in ocean mass and volume. On the lower left, you see the GIF shows you when the ice melts, the same amount of the melted ice goes into the ocean and causes the sea level rise. And on the lower right, shows you the sea level rise due to the thermal expansion. As we know, since the Industrial Revolution, the global mean temperature rises for about more than 1.2 degrees Celsius, so which we will call the sea level to rise. And also keep in mind, for Greenland and Antarctic ice sheet, we stored over 67 meters of the ice equivalent sea level, which means if they will melt, the global mean sea level will rise for 67 meters. And here shows you the regional driving processes, the response to the ice loading and redistribution of water. On the lower left, which is the classical glacial isostatic adjustment GIF, which means when we have the large ice sheet, it will depress the surface, and the surface will subside due to the load. Like this, when they grow, they subside and push the mantle material flow outwards, form a forebulge. During the deglaciation stage, since the LGM, when you remove the load, the beneath the load, the surface will rebound. The mantle material flow backwards, and the forebulge will collapse and also migrate. On the lower right, this shows you the so-called the sea level fingerprinting, or they call the gravitational, rotational, and deformational effects, which mainly affected by the gravitational attraction between the large ice sheet and the ocean, which means when the ice sheet accumulate, the gravitational attraction will be stronger and the water will pour towards the ice sheet. On the contrary, when we have the ice melt, then the attraction will be weaker. Then you see the sea level will fall in the near field region when ice melting. So where does the extra melting ice goes? They go to the equatorial region mainly. So here shows you a distribution pattern due to the contemporary ice melting in Greenland ice sheet and West Antarctic ice sheet. So you see this scale means the ratio of RSL change to global mean sea level change, which means if you have an equivalent of 1 meter global mean sea level ice melting, then how the relative sea level will change at a geographical distribution across the globe. You see, for example, for Singapore, if the Greenland ice sheet melts for 1 meter, and it will experience 1.3 meter, which means for Singapore, it will experience 30% more the sea level rise when compared to the global mean. So as we see, both for the Greenland and Antarctic, the meltwater is distributed unevenly, and the tropics are especially vulnerable. Here shows you some representative local driving processes, such as the local subsidence, tectonics, and the ocean dynamics, the monsoon. For the lower left, the figure shows you the land subsidence caused by the groundwater extraction, such as now the experienced city like Manila or Jakarta, they suffered from this, and the land subsidence will further accelerate the sea level rise. In the middle, shows you the tectonics, such as the interseismic deformation, co-seismic deformation, and post-seismic deformation, where will change the land level and cause the sea level rise or sea level drop. And lower right shows you the monsoon influences for the sea level change, such as when we have the south wintry northeast wind, then you see the sea level will fall in the Southeast Asia. On the contrary, when we have this level rise in this region. So next, I will talk about the past sea level change. So for the past sea levels, how do we measure? So our understanding of the past sea level changes derived from combinations of sea level index points from proxy environment and indicators. So I know many of you may are familiar with this, so I won't go details. As for the coral reefs and atolls, which are widely distributed across the Southeast Asia, so they can reconstruct the sea level, recorded the past sea level history. For the rest of the species are mainly in the uplifting regions, such as the North America and Northern Europe, which previously covered by the large ice sheet. And for the oysters, which mainly record the sea level fall from the headstand. And for the mangroves and salt marshes are widely used in reconstructing the perennial sea levels, such as mangroves in the coastlines along the Southeast Asia, including Indonesia and also Singapore. The salt marshes are mainly in the mid-latitude region, such as the Atlantic coast of the North America and Northern Europe, and also the high latitude region. Next, I will show an example from Singapore. From Singapore in years, we investigated new sites using the geological records, such as mangroves and coral microatolls. For the mangroves, we tried in 2 sites, such as the Jurong Lake, and also in Palau Ubi. We have the graduate students. They're working on the course we took from the Palau Ubi to reconstruct the sea level change since the Mid-Holocene headstand. We also have the coral microatolls found in Sentosa Islands and Lazarus Islands that will help to fill the gap we have since the Mid-Holocene until present. So here shows you how we reconstruct the perennial sea level using an example of mangrove sediments. So for each sea level index point, it must have 4 key information. The first, you must load the location, and then the altitude, age. Most importantly, you need to load the relationship between the sample and the modern tether level, which is also known as indicating median or indicating range. So here shows you the example of mangrove sediments. Normally, you can use the microfossils, such as the foraminifer, to study the modern distribution of the species and abundance. And then you do the analog to the core we took from the field and to reconstruct the sea level indicators. We have 3 types of sea level indicators. The sea level index point, which can tell you the information about the sea level at a certain time period and with a certain elevation, with corresponding temporal and elevation uncertainty. and also the terrestrial limiting data, which provide you the upper bound of this level, which means this level must be below the terrestrial limiting data. And similarly, we have the marine limiting data, which provide the lower bound for the sea level. The sea level must be above the marine limiting data. So for the glacial isostatic adjustment modeling, which we normally use to compare with the data, how we model the GIE process, we have two inputs: the Earth model, which describes the density, elastic properties, and most importantly, the viscous structure of the Earth, including the mesospheric thickness, the mantle viscosity, and the ice history model, which describes the ice thickness coverage and their temporal evolution history. I use the finite element model to solve the sea level equation and also consider the rotational feedback of ocean and ice load. Because I use the finite element model, so I can simulate the lateral viscosity variation, which known as the lateral heterogeneity. For the traditional spectral normal model method, they can only assume the viscosity or the Earth properties very laterally, but they can only simulate the Earth to very radially. They cannot simulate, they assume it's homogeneous laterally. But for my model, I can simulate the more realistic Earth, which means the very laterally, such as the subduction zone in Cascadia region. They can achieve the goal of the 3D physical structure, the geometry of the subduction zones. And we have the outputs of the sea level predictions and also the surface motion, including the horizontal motion and also the vertical line motion, the gravity field change, the Earth rotation, as well as the GIE stress evolution, which may cause the post-glacial seismicities. So actually the GIA will include the three chief figures shown here, the processes driving sea level change I mentioned before, the ice melting, the equivalent ice goes into the ocean, which you may understand as the ice equivalent sea level change, and the isostatic response, which will vary from place to place across the globe, which the main pattern of the GIA is the vertical line motion, driven by the vertical line motion due to the ice loading and unloading. And third, the gravitational, rotational, and deformational effect of the ice melting. So all these three processes are included in the GIA modeling. Here shows a model output of the pioneer sea levels since the LGM, the last glacial maximum, till present. As we see, at the last glacial maximum, such as 26,000 years present in the S6G model, the Northern Europe and the North America, they're all covered by the large ice sheets of over 3 or even 4 kilometers thick. And when this ice melt, you see the global mean sea level will rise about 130 meters. And adjustment of the land to the unloading of the ice and redistribution of the melt water will cause distribution variable sea level changes. Here we choose 3 sites, which is known as the Hudson Bay, the near field region, and the second, New Jersey, which is just close to the previous ice margin, which we classify as the intermediate field. And third, in Singapore, or the whole Southeast Asia, they have some similarities called the far field region, which are the location which are far away from all the large ice sheets. So for the 3 sample sites, they experience totally different sea level change histories. As you see here, for site 1, which is the Hudson Bay in the near field, because when you remove the load, the land will uplift. Although the sea level, the global mean sea level is rising, the land is uplifting as much fast level is falling continuously. Sorry. And for the site 2, which is the intermediate field in New Jersey, when we remove the ice load and the forebulge will collapse and subside due to the subsidence, the sea level will keep rising in this region. So you see for New Jersey, the sea level keep rising until present. For the far field region, before the mid-Holocene, will be dominated by the melting ice source. So we have this sea level rise. And during the mid-Holocene, we reach a high stand, which mainly caused by two processes. The first is the equatorial ocean thickening. When we have the forebulge collapse, the collapsing forebulge will accommodate more water transferred from the equatorial region. Meanwhile, in the shallow continental shelves, like Southeast Asia, when you have this level rise, the rising load will depress the sea floor, and you have a tilting effect. So due to the continental leveling, offshore you have the subsidence, and onshore you have the apneas. Then you will cause further accelerated sea level falling. So we have the mid-Holocene high stand, then sea level falling to present net day level. So here shows you a zoom in of the pioneer topography change in Southeast Asia. As you see, as sea level rise, it flooded the land bridges connecting the Sumatra, Borneo, and Malacca Peninsula, and reduced land area by over 50%. So if we look at the pioneer topography at different time points, you see from 26 until present, you see how when the land were flooded. And on the upper right, you see it's a calculated land area difference relative to present day topography. And also the dotted line here shows you the ice equivalence level from 26,000 years based on the I6G global ice model. So we see the ice equivalence level rise for around 130 meters. Especially there are two rapid melting events, which is known as the melt water pass 1A around 14,000 years to present, and 1B event around 11,000 years to present. We will also take a transact, as you see here, from Singapore to the Sanda Shelf, to the center of Sanda Land, where we have the data, the pioneer data from Heimberg's paper. And for this transact, we see since LGM, we have the average lateral shoreline migration rate of 57 meters per year. And during the meltwater pass 1A event, the lateral shoreline migration can increase to over 300 meters per year. So here shows you the past sea levels for Singapore of Holocene sea level change action back to around 10,000 years in 1 meters at 9.5 kbp to a high stand of magnitude around 4 meters, about 5,000 years before present, and then decrease to present level. And then we see the sea level rate decreased a lot since the early Holocene, which is when the ice melting source from the large ice sheet stops or slow down first and then stop. You see when the sea level fall, we have a elective rate of sea level. Although we show here see some low stand of this, but due to the large uncertainty, the vertical uncertainty, this is still possible if there is a low stand. Next, we combine the data from the Sanda Shelf, from the Sanda Land, and Singapore together, even include the data of the tide gauge in Singapore in the instrumental time period. So you see the shaded green here, which indicate the micro-ATO data. I will introduce more later from Singapore and Macau. So when we use the statistic model, the EIV IGP model, the errors invariable integrated Gaussian process model, we see how the sea level change in Singapore since about 20,000 years to present. We see how they change during the LGM is about minus 120 meters, and then during the deglacial transition, and the sea level keep rising until in the early to mid Holocene when sea level stabilized, and due to a big data gap here since the mid to late Holocene. Then sea level close to present, and we see a recent acceleration, sea level rise. And you may notice here we see the sea level change rate are lower during the meltwater pulse 1A or 1B event. That's because here, when we do the statistical model, we don't have much data to allow the very high temporal resolution. So we choose 250 years of the time interval. That's why you see for even the meltwater pulse 1A event, the rate can only like 20 or 25 maximum. As we said before, we see a gap of the mid-Holocene high stand to late Holocene. Actually, this phenomenon is also common in the whole Southeast Asia. The high stand timing and also the magnitude a lot well constrained. So here, what I'm doing now, we have an ongoing study. We try use the GRE model to test different parameters. Then we run an ensemble of the GRE models. We get an average and also the standard deviation of the high stand prediction. And then we take the present day topography, the bathymetry maps. We try to derive the paleo topography change. And then we identify the locations that previously they are flooded by the sea level during the high stand, which means they are below the past sea level, but now they're above the present sea level, which means they have the potential to record the high stand. They must have the high stand preservation. Here you see all the red dots. They are the locations we identified that they should have the high stand preservation, which means if you want to do this level reconstruction work, you should go this place, and then you should be able to find the high stand preservation and reconstruct the high stand sea level data to better constrain the timing and magnitude, and also the spatial variability of the high stand. And here you may see the dots of the purple, green, and blue. They are for the purple and the green, they are the high stand records that in the publications, they say they have the high stand and they are matched with our high stand, the treasure map, which means the map is valid, including the latest publication from the Luden Java from Thomas Mann et al. In geology. They say there's a high stand and the treasure map of the high stand, they match here. And for the Archer, we say they shouldn't have a high stand preservation. And the study done in geology also, Kasi, they reconstruct the sea level history there since the early to mid Holocene until the present day. They didn't see any high stand that matches well with our maps, which means this map can give the field scientists some idea to guide the future sea level collection efforts, where they should go, where their target area. But for here, you may see for the Mekong River Delta or Bangkok, although, especially for Mekong River Delta, they have a very dense distributed red dots, which means they should have the high stand reservation. But due to the intertidal flooding, well, they have this region experience the significant subsidence. So which means these records may be submerged and they are lower than present. But if you compare the data with our prediction, you can resolve the misfit, and you can to estimate the subsidence rate in the geological time scale at from early Holocene to mid Holocene or even till present. Here we mainly try to find the location where you have the high stand preservation, and we also try to compare the magnitude. You see the blue indicates the J prediction within 2 sigma uncertainties, and the red, we have the slip, marine limiting data, and terrestrial limiting data. You see actually they fit pretty well, except for the theta 1, which is from the Bangkok. They have a very exceptionally high slip, and we suspect there are some local influences leveled up these sediments. That's why they show very obvious misfit. Apart from this one, the rest all match with the prediction. And one more thing is the data, because the slip, they're only one data point value. They're not a very continuous time series, can show you the whole sea level history. So the high stand magnitude must be equal or higher than that slips. Unless you have you see the sea level rise first and then falling, then you can locate the mid Holocene high stand, the timing and the magnitude. That's our target with more data available. The next is our group work that they previously done with the news level records and also the records of the preservation of the absence of absence and presence of the salt marsh and also mangroves, they try to find a threshold value for with a very likely range, like 9% probability, whether they can keep pace with the sea level rise, whether they can survive or not for around 7 million per year for the salt marsh and also for mangroves in the far-field region. Here it's about 7 million per year, which means, so what that means? That means when the sea level rise is lower than that tipping point, then the mangrove forest can keep pace vertically with the sea level rise. However, if the sea level rise exceeds that tipping point value, then the coastal mangroves, they cannot survive. They will be drowned and the forest will retreat landward. So this had some implications for the mangrove restoration. That for Indonesia, the government they tried to restore more mangroves in the coastal region. Then here to a very important information where you should go. And also you need to investigate whether the locations they are likely to experience the further subsidence in the future, because the subsidence will further accelerate the sea level rise. If they exceed the tipping point, then the mangrove there, they cannot survive. So next, I will talk about the present sea levels. As you may know, the present sea levels are mainly recorded by the instrumental measurements using the tidal gauge records, using the upper, and also the satellite altimetry data. For the tidal gauge, they are heavily unevenly distributed across the globe, mainly in the northern hemisphere. From the past tidal gauge records, they reconstructed the estimated sea level change rate at a different time period. As you see here. So here needs to like the studies in the past like 20 years or so. And you see, we do a summary in the Horton et al. In 2018 paper. You see a clear rate of sea level rise. Sorry, this is a bit slow. If you go back to 1900 to 1970, the sea level rate 1960 to 2006, the rise to 1.9, and more recently it's about 3.7 million per year. The studies they say you see in the red, they are mainly before 1970, the rate or 1990, and for more recently, the sea level rate is more around 3 or even larger millimeter per year. So we see a clear sea level rise acceleration since the Industrial Revolution. So here shows you the tidal gauge only for the records longer than 40 years. You may notice in Southeast Asia, we only have a few tidal gauge stations that can date back more than 40 years. Then how can we go to know the sea level change history before that at a higher resolution? So here shows you the tidal gauge records in Singapore. As we see, although we have quite a few the tidal gauges around Singapore, they can only go back to 1970. If we want to know the information at a higher resolution, back to even 1950 or 1920, how should we do? So our group, they try to use the proxy reconstructions of the coral microatolls, which are very high resolution, both in spatial and temporal. So they try to use this to extend with the instrumental measurements. The coral microatolls, they will grow within the sea level, and if the sea level drops during the annual low minimum, the low water, then they will die. Part of the edge will die. When the sea level keep rising, they will grow again, and they say there's a die down. The die down can record those low water, and if you date that die down, you know and also survey the elevation, then you can reconstruct the one sea level index point in that at that die down. And if we have a series of the die down, and then you know the series of the sleeves with high spatial and temporal resolution. So here our group did a study for try to extend the sea level records in Singapore. from the tidal gauges with microatolls from Singapore and Nepal. As we see here, we extended the sea level back to 1910 or 1915. And this level, we found this level was stable, about 0 plus minus 1.6 millimeter per year from 1915 to 1990. And after that, its level increased to 1 plus minus 2.1 millimeter per year. And most importantly, you may also see here, the uncertainty decreased by more than 50% from the light green you see here to the blue. So next, I will talk about the sea level, future sea levels based on the IPCC AR6 scenarios. So the sea level projections from IPCC, they are mainly the scenario based from very low emission scenarios, SSP 1.9 to the highest emission scenarios, SSP 8.5. And I will mainly show the likely range, which represents 17th to 83rd percentile, represent a probability of at least 66%. So here shows you the global mean sea level. As you see here, the median value shows this level will rise by about 0.38 meter and 0.77 meter under the SSP 1.9 and SSP 8.5 scenarios. Here shows you the likely range. They can be over a meter at the SSP 8.5 scenarios. So how about Singapore? So Singapore experienced a very similar magnitude of sea level rise compared with the global mean. And if you look at the rate, you see under the SSP 1.9, namely about 3 millimeter per year by 2100 and more than 12 millimeter per year by the end of 2100. So that's for the IPCC AR6, there was probably a scenario that to indicate the potential impact of deeply uncertain ice sheet processes for the Antarctic and Greenland, mainly Antarctic, so which we call the high impact, low confidence, but high impact scenarios, which are all the same as the SSP 8.5, except they incorporate the Greenland and Antarctic ice sheet process, for which we have low confidence, but we cannot rule out that scenario. Mainly from two processes. They are the marine ice shelf instability and marine ice cliff instability, which is also known as the MEISI and MEICI process. So for the MEISI, which is marine ice shelf instability, is due to the ocean currents, and for the ground-based ice sheet, we will see the grounding line retreat, which will further accelerate the ice melting and contribute to the sea level rise. And for the on the right, you see the marine ice cliff instability, which is because of the cliff failure due to the hydrofracturing, and then the cliff will further melt in the ocean and accelerate the sea level rise. Here shows you a short video our group took from the Antarctic. You see all the fracturing, hydrofractures here. So if we consider the high impact, low confidence, high impact scenarios, from here you see the sea level can rise up to 0.92 meter by the end of the century, and the rate can almost over 19 millimeter per year. Another very important information for the projection is about the projected timing of the sea level rise milestones, which means when the sea level rise rate will exceed a certain magnitude, like for half meter on the upper panel and 1 meter in the lower panel. You see the magnitude 0.5 and 1 thresholds under SSP 8.5, as you see here, the brown color, they may surpass by 2018 and 2120. And this timing are very important for the adaptation and the mitigation strategies, which means when you make the plan, you need to have a target, whether you are making the plan for the next 10 years, 20 years, or 15 years, then you have a estimated the projected magnitude of the sea level, how high they will rise. And here is a combined study of previous issue. We combine the data from Singapore and the Sunderland and have a continuous sea level time series since the navigation maximum to present. And then we know how this level is likely to change in the future in Singapore. And the different scenarios, we take 2 scenarios here for SSP 1.9, so which means they will rise to 3.4 millimeter per year, and also the SSP 8.5, which means they will exceed 11 millimeter per year. So what we're doing here, we try to estimate the sea level rate in the past and provide a deglacial perspective of future sea level rise, which means if future sea level rise by this value, such as 3.5, whether that happened in our geological history and by how likely. So here, as you show for the 3.4 millimeter per year under the lowest emission scenarios, we are virtually certain they had occurred between the 15.25 and 13.5 thousand years before present, and also between 9.5 here and 8.25. However, during the last 5,000 years, it is unlikely the rates of RSL rise exceeded 3.4 millimeter per year. Similarly, if we consider the SSP 8.5 scenario for the 11 millimeter per year, we see this level were unlikely between 21.5 until 15.75, and it's likely to happen from 15.25 to 14.75, and virtually certain around 9,000 years before present. And most importantly, during the last 8.25 thousand years, it is extremely unlikely rise of sea level has accelerated, has exceeded 11 millimeter per year. So to summarize, as our Prime Minister said in National Day Rally in 2019, we must prepare for the impact of climate change, and Singapore is especially vulnerable to one grave threat, and that's the rising sea levels, especially under the condition that sea level is such a small island with 30% of the land less than 5 meters above present day sea level. As you see on the lower right, the G figure shows the sea level rise itself will accelerate the corresponding the coastal flooding, the storm surges, because they provide the baseline of the water level. And if you consider also the tides, the waves, and the coastal erosion and storm surges, all the coastal hazards will be accelerated. The frequency will be higher and the return period will be lower, which means previously maybe a 100-year event may become to 50 years event or even 25 years event. On the upper right, you see is an example about the compound flooding. If we have the high tide and also have the very high rainfall, high precipitation, and then you have the compound flooding, which will magnify each other, and you see all the streets, the urban areas were flooded. So the past and present records of sea level, they have varied in response to a wide range of the processes that controlling the sea level change. And with more data available, we'll better understand these processes, and that can help to constrain the future sea level and also to narrow down the uncertainties. And the ice mass loss from the glaciers, the Greenland and Arctic ice sheet, they will contribute to the sea level rise in the 21st century under all these scenarios. And the sea level will continue to rise throughout the 2100, and in Singapore, by the end of the century, the sea level will be 0.37 meter under the lowest emission scenarios, SSP 1.9, and 0.78 in the SSP 8.5, and even 0.92 meter if we consider the low confidence, high impact scenario. So the higher amounts of this level before 2100 could be caused by the we call the MISI and the MITI, the marine ice sheet instability and the marine ice cliff instability. So such process could be contributed more than additional meter of sea level rise by 2100. So all this, the summary and the information for Singapore and also applicable for the cities around Southeast Asia, they facing the similar situation, especially they are all have the very large area, lower lying coastal zones. That's all my presentation. Thank you.
Thank you very much. That was very nice. Beautiful graphics. So I really enjoyed that. I don't know, Yuda, do you think we have a round of questions now, or we proceed directly with Hilim's talk?
I think maybe it just proceed with the next speaker. Then after that we can have a question.
Okay, sure. Sounds good to me. Then we
Right.
like that.
Wondering,
All right.
one question, Yuda. It's important before the next speaker, I think.
Yeah, go ahead.
Yeah. Okay.
Okay, it's up to
Thanks,
you.
Yuda. Thanks, Yuda, because it's very important. I think it's very important to me also and to everybody. Tang Hua, in your graph, you know the younger rise, right? The silver rise from LGM to about, during the MWP01B, about 14,000, the sea level rise dramatically, and then, in about 12,900 at the onset of younger rise, the global temperature dropped again, so the sea level drop again to the LGM sea level for like 1,300 years before it rise again dramatically at the end of the younger rise, MWP1E. So on your graph, this younger rise, it's not showing. Why is that? It's very important event. I'm just suspect that because you extrapolate data from 14,000 through 10,000, you don't have data between 14,000 to 10,000 data. Is that correct? Thank you.
Yeah. Yes. For your point, first for the GI model, the ice history model, we use the openly free available, the I6G latency model from the Toronto University. And for the data, as you see, we take from the one part is from Singapore. They only have the Holocene data. And the one part is from Sunderland. They only have the data back to 13 or before that, mainly for the meltwater pulse 1A event. There's low available data for the meltwater pulse 1B event. You are right. That's why we cannot see there should be like a massive stop during the younger rise and then rise again.
Okay, so just ignoring the younger rise on your graph, yes?
Yeah.
Okay, thank you.
Okay, I guess we can proceed. So, Hilim, the floor is yours.
So can you hear me well? Okay, good.
Yes, we can hear you.
Then can I ask how much time I can have? Probably run out of time. Is it still? I'll try to make it as short as possible. So everybody can see my slides.
Yes, I think so.
Thank you. Thank you. Thanks so much for your invitation. This is such an opportunity for me to give a talk today for the audience in BRIN. Sorry, I couldn't visit there, but hopefully next time I can have a time to visit there and meet with you. So today I'm going to talk mainly about the impact of the sea level change, which already Tang Hua extensively explained. So I'm lucky I don't need to explain about that today, but today I'm going to talk more about the human history. And before I start to talk about it, I briefly talk about this project we are doing here, Genome Asia 100K, which generate the data set I used for the study. So this is a large-scale human population genome project. which is done by the this consortium, which is non-profit organization. And this collaboration is over 26 research institutes in 11 countries. And NTU, our university, is one of the founder member who generate the data and analyze the data for the sample provided for over these collaborators. So the project aims, it's very straightforward. We want to generate whole genome sequence data of many Asian samples, which will contribute to human genetic study and the development of precision medicine for Asian population. The reason is pretty simple. Still, there are a lot of bias in the public database or the human genetic study. There is a much less of Asian ancestry samples, despite of the large proportion of Asian in the world population. So Asian population cannot benefit from the result of human genetic studies. So that's something we want to change in this field. And since our first publication at the end of the 2019, we published several papers, and we also published our data in this database, which is public. Everyone can just access and see the frequency of the genetic variants we found from the data set in there. So today if I introduce a bit about the sample distribution here, the main interest of my group, especially for my group, is the covering of the genetic diversity in Asian. So it's very diverse group, and we already covered more than 450 ethnic groups. We have this humongous data set analyzing for many kinds of research questions. One of my biggest interests is, of course, the genetic diversity. So this is called the mixture plot. The first result I can explain you from the population genetics. One each bar means one each individual, and the color represent their genetic ancestral component. So if you see some of the population have only one color, but some of the population have mixed up several color, means they have multiple ancestral component because of their complicated history. So you see many colors, especially in Asian. If we compare this complicated ancestral structure to the public data set, which is from the 1000 Genome Project, this is the most commonly used in the human genetic study. So compared to their coverage for Asian, ours are it's not comparable. Our genetic data, even smaller number of samples, it covers much diverse population, which reveal their true genetic diversity and history. So again, from this genetic diversity, from this ethnic diversity, we have what kinds of questions we can have. I'm focusing on their environment. Humans are very strange species. It's only species occupy all continents in the world. So it means their adaptation, genetic adaptation in those various environments, from the frigid area to tropical rainforest. So I'm very interested in how our genome adapts on those environments. At the same time, environmental change, which is sea level changes, as Tenga already explained. So one of the most dramatic sea level changes happen from the LGN around this area in Southeast Asia, which was huge, and I was interested in how human respond these dramatic changes. So luckily, we have sample who can tell us the history. Okay? It's very important. So I'm trying to explain who they are here. So this plot shows our sample distribution, which includes the earliest settler in South Asia, the red color people here. One of them are, or we call them South Asian Austroasiatic because they speak Austroasiatic languages. They live in the forest and tribal people living in Eastern Asia, India. The other, the earliest settler in Southeast Asia, they are still living in Malay and Philippines. Kansiu and Kintak people called Malaysian Negrito. They are hunter-gatherer. They are one of the minority living in the forest of Malaysia Peninsula. And we have a long-time collaborator, Kai. He visit the villages and he stayed there long, couple months and became friends. He collect a sample from them and provide it to us to sequence their whole genome. ETA, Philippine people, they also called Philippine Negrito. They have a very short statue, about 140 centimeter. Our collaborator, Michael Ellingham, he went there and he did a medical checkup as a volunteer. And then he collected the sample from these people because he's eye doctor and he was interested in this population. They never have a glaucoma. So those collection of DNA, that's I collected. Okay, so our project collected the DNA collection and we collaborate those people who have the samples. Here are Dai. They are actually originally from Thailand. They're living in the very southern part of China. So I put them as a representative of mainland Southeast Asia. So including these people, we have more than 700 whole genome sequencing data from 59 ethnicity in this area. And then we try to trace their history from their genome sequencing data, okay, over 20,000 years. So we need the people who lived in this area for a long time since LGM. Okay? So this Malay Negrito, Philippine Negrito, or the South Asian people, they lived in here over 50,000. That's why we could trace back their history. Otherwise, we cannot really trace the history. So now you know what's this plot. I look at their genetic ancestry and let's see this Kansiu, Malay Negrito people, they have only one color, so they have a very distinct ancestral component. But interestingly, the other population, we also found this blue component, partially. So it's not surprising we find from another Malaysian people here, but we also could find from the Dai and even in South Asia. So that was completely unexpected. And I wanted to find out the real story, how they could have the Malay Negrito ancestry in their population. So here I'm going to show you another evidence again and again and again, because in this field, it's very difficult to appreciate the reviewers. So I tried all the possible way. So this is a slide to tell you we have something sophisticated method to trace this inference of the population history using their genetic variants. We see their common ancestor and we estimate their time, and from the distribution of the common ancestor we can reconstruct their population size over time. Okay, and another method tells us their gene flow, the migration rate between the population also over the time. And then we can inference their population history. This is the migration rate between a pair of population. You can see it, the Malay Negrito, below is the South Asian. So they once split. So the drop of the migration rate said their population split long ago. And then after the split, they have a little peak of migration rate again, means they met about this time. So the resolution of the genetic analysis for the, especially for time estimation, is still broad compared to geology, I would say. But we could see it's about the 10,000 years ago, they probably have a gene flow between the population. We found the same peak around the same time, again, between the Malay Negrito and mainland Southeast Asia, Thai people. We also construct their population size. So this is from past to present. They once increased and had a peak of population size, again, about the same time. So their population size expanded over like 5 times. But if I see the population size in South Asia, they also increase, but not only increase, the peak is completely over. This is not population expansion. This is more about the mixture, which is there is probably introduction of the gene, very distinct genetic ancestry from outside of their population. That's why they have a peak of this population size expansion. So if this is another method again to prove that there is a migration gene flow between the Malay Negrito to South Asian population, about 30%. It's based on the modeling, and we tried all the combination of other population source, and the best fit model is between the South Asian and the Malay. So from the Malaysian Negrito, that's the important thing we showed here. So now I can say that there is a gene flow from Malay Negrito to South Asian. But interestingly, this gene flow is biased between male and female. We see autosome, there is a blue from the Malay Negrito, but no in X chromosome. There is a more ancestry in male than female. So, which is male-driven migration. It's also supported by the comparison between mitochondria and Y chromosome. We see the Y chromosome specific from Malaysian Negrito and found in South Asia, but not in mitochondrial DNA, which is only from the maternal lineages. Another interesting thing is about the population split between within the Southeast Asian specifically. They split about the 14,000 years ago, or at the same time between Malaysian, mainland Southeast Asia, and Philippines. Okay, so if I combine all this history, and then here it's important, can God help us to estimate the land size, and I wanted to compare between the mainland and Ireland, Southeast Asia, because we see this population, Malay Negrito, go into the Thai and also South Asia. But we don't see the gene flow from mainland to South Asia. So if I compare the land size over the time, the decrease of the land size between mainland and island. Also, I added up the population size we estimate based on genome data, and we calculate the population density. Then there is a higher population density in island part rather than the mainland Southeast Asia. Both increase the population size, but the reduction of the land size is much severe in the island. So probably they have a higher pressure to stay in in that area. So we see Malaysian Negrito, ancestor of the Malaysian Negrito, they probably migrated, forced to migrated to the continent's direction, and some of them stay in mainland. That's why we see the mixture signal in dye, and some of them keep migrated to and reach it to South Asia. So this might be the story. So if I summarize this story, let me play this. Probably I don't play the sound. So in the beginning, there was a Sundaland, a big chunk of the land, and the common ancestor occupied that area. After the rising of the sea level, first they split, the population split occurred because of the breakage of the land and island. And then later, even after the more sea level rise, they migrated out and mixed with other population in South Asia. So that's the short summary of the finding as a response of the climate changes, sea level rise of human populations, on human population. So I want to highlight that this study is showing the impact of the environmental change on the human demographic history, which happened long ago after the method first 1A and 1B. But at the same time, it's remained it changed the genetic background of the modern population. We still see the difference in the modern population. It's make population split, which means the divergence of the population in Southeast Asia increased, and it makes a mixture between the populations. So South Asia having this portion of Southeast Asian component, which changes their genetic background, which also impact on their profile of the health status of the modern population. That's something I wanted to highlight from this study. One another, that's not what I wanted to see. So if I edit only one more slide, the sea level rise, it's not only impact on the human, it also impact on a lot of other organisms, as Tengua mentioned, from the mangrove and so on. So here in our group, we are also looking at the sea turtle genome data. So we collected the sea turtle egg, the unhatched egg, and extract the DNA and see their population history. It's only one result I show. This is the population size changes of the sea level sea turtle. We collected from Singapore. We see that this sudden drop of the population size from the LGM. So it might impact on the sea turtle also, because these have very unique habit. They always coming back to the nesting sites they were born. If they cannot find the site, their place they were born, they select, they make a decision not to lay eggs. So this environmental change impact a lot to sea turtle, of course. But that's something I wanted to share with you in addition to the human history. Okay, I think I'm stop here. Thanks so much for your attention. Let's see how I. Yep.
Yeah, thank you so much, Hilim. That was great as well. Really interesting. I learned several new things as well.
Thank you.
So to the audience, everyone, first, before we move to questions, there is a request in the chat box to fill in the attendance list. with a link as well. So if you could all please do that, I'm sure the organization will be happy. I think already earlier I saw there was a question by Albert Suleiman. Is he still here? Maybe not. Ah. So I don't know. I propose that anyone who has a question can use this raising hand. Okay, go ahead, Danny.
Okay, thank you, Tino. Okay, question for Dr. Kim, Alan. First question, for the people in Java and Sumatra, Sundanese, Japanese, Malays, is that classified as negrito on your scheme? Or?
Oh, no. If you are asking about the people in Japanese, we don't have the sample, so I cannot answer the question based on our genetic data. But as I know these people, I actually analyzed the people in another data set, and most of the people from the Western Sumatra, they are Austronesian. Of course,
Hawaii.
they are
Referring to Hawaii Island. Not Sumatra, Malays as an
Malay Island.
Okay. Anyway, second question. Yeah. The mitochondria DNA research cannot really tell the quantity or the size of the population, right? It's just a relative population. So I see your graph that the population increased from LGM to Holocene continuously. And I see also in the paper I read, there are a significant increase, like 5 times or even 8 times after the late Pleistocene increase in population. So again, I'm asking about the size of the population. It's a relative, right? You cannot tell the size of the population in the early Holocenes with the size of population, say, in 13,000 years ago. So it's a relative size, right? Because the DNA research cannot really tell the quantity of the population.
You're correct. So this is based on the whole genome sequencing data, first of all, not the mitochondrial DNA. But even we have the whole genome sequencing data, we cannot the population size I mentioned is effective population size. This is not a census size. We cannot tell the census size. It's probably the archaeological area. So effective population size is not same as census size, but it correlates with census size, of course. So if the census size increase, effective population size also increase, which is about the diversity of the genetic. Their genetic diversity. So effective population size improves based on their genetic diversity. If the census size decrease, then the effective population size also decrease. So I'm telling you here it's not the absolute size, but it's the theoretical size based on the genetic diversity. So it's not exactly relative, but the diversity increase as same as the population size. So here I tell you about 5 times higher or 6 times higher compared to their previous population size, which is completely about their genetic diversity. So increase is increase, yeah.
Now it's a very general question. Is your research support that the Sundaland ancestors always remain in Sundaland since LGM? So the ancestors is always in the LGM, and after the late Pleistocene, the people from the Sundaland go outside, like out of Sundaland to the Southeast to the Asian, right? So it's really support the theory of the out of Sundaland instead of like out of Taiwan, that the ancestors of Indonesia is come from the Taiwan that come to Indonesia like 5,000 years ago. Can you?
Yeah, there is a
say something about
hypothesis about outland Sundaland. I'm very happy to help your question, but this is much older than that hypothesis. So that Sundaland outside of the Sundaland hypothesis about the Austronesian expansion, but this is about Malay Negrito, which is the different people, and our expansion is older than their hypothesis. So I think it's a two different story. So we don't support their hypothesis because it's about the different people.
Perhaps you can explain what is the difference between your results with, for example, Stephen Oppenheimer.
Stephen Oppenheimer, what about his?
Stephen Oppenheimer also tell the story about the Sundaland ancestors that's always in the Sundaland, and then they go out of the Sundaland because of silver rice. Go out of the Sundaland.
Yeah, again. So we actually compared a lot of this previous study in our manuscript. Most of them, including his study, they don't even have the sample from the Malaysian Negrito. So they probably didn't have a chance to look at this history. So that's first thing. And the second thing is most of the previous history, as you mentioned, they based on the mitochondrial DNA or Y chromosome. So it doesn't give the resolution of our study, of course. And then they have no resolution to trace back this ancient history we showed over 20,000 years ago and the time estimation. So that's basically very different. I would say very different. But I understand many of them try to explain about the response of the sea level changes at the same time. Some of them try to explain the population moved out across based on the mitochondrial DNA. But most of the study is about more recent history than we suggested, or the direction of the migration is different, or the origin of the population is also different.
Okay.
Yeah, of course, the population history is very complicated, especially in this area.
I think it is very interesting. I think it's good to also like give the chance to some other people to ask some questions. I've seen Marfazran with his hand up for a while.
Yes, thanks. Hi, Helen.
Hi.
Yeah, it's interesting that I work on the climate during the last glacial period in Indonesia, actually, and that's my question. I think it's other perspective than the sea level rise. Why the Negritos Malaysian that you said that moved from Sundaland to the South Asia. What do you think about the possibility about the extreme weather? I mean, during last deglaciation, we find that a long periods Heinrich event and also younger dryas, and is not mentioned in the record of sea level. And I know that from the record from the climate record during like MWP1B, like increased precipitation during like very abrupt, like 400 years ago, 40 years, 40 years, yeah, 40 years, very abrupt. What do you think about that one? It's related to the extreme weather, the reason of the Negritos move.
Yeah, thank you so much for your question. So we also try to find out another climate change, not only sea level rise, about the migration, especially for the period of the time they migrated out. But so that's why I have a Tengua and other author in our manuscript. So according to them and the literature, we try to find out the temperature rise is not that high in this area, not too much difference, only 2 or 3 degrees. So it's not extreme changes, first of all. One other our colleague said it's more about the monsoon changes rather than the temperature, but it is also not too extremely different. But at least we see probably their changes is not negatively working for human population. It is more about the more preferable. So it actually supports the population expansion there. So the condition during this deglaciation probably helped them to expand their population size. But instead, the flooding and the land size decrease a lot. So that might be the force the human to moving out from the area because of their increase of the population size.
The population size.
Mm.
Yeah, but I mean, like even like you mentioned, like I have the SST increase like 3 degrees Celsius from last deglaciation. I mean, but the main record, like in Indonesia, we find that the region in Indonesia, like today, so for example, today in Kalimantan is very wet because it's very in tropical area. But during the Heinrich event, Younger Dryas, and we find that many, I mean, main region of Sundaland is dry, very dry. It's very very different. That's why I asked you, but could be it's this very dry condition like during last deglaciation like around of 5,000 years something could be you could consider about that's climate during that period. I mean,
well, maybe Tengua, do you have any other idea to answer the question?
okay. Maybe.
Yeah.
Okay.
I think for the monsoons or the Younger Dryas you mentioned, it's more like a once event, just a very short time period, or they won't happen like the sea level continuously. Another thing I would want to say, emphasize about the resolution, the temporal resolution of either the genome data and also for our model itself. Because if that happened in the history and that won't affect the sea level, then the sea level change won't reflect that factors. Also, if the temporal resolution of the genome data, as you see, they may say there is a offset between we don't match perfectly well because the uncertainty both for we use 500 years interval, which means the sea level change is pretty large. If you look at the Younger Dryas or the method plus 1A or 1B, which means that's why we cannot resolve the details. The same for the genome data. I don't know exactly how the resolution for the genetic data, but I guess it will be very challenging based on the current data set. You want to resolve the very detailed information for one event. Unlike the geological records for the tsunami or the storms, you can even locate within a year. But I guess for the genetic data, it's too challenging for that.
Yeah, okay, I can add up that. So unless the population, I mean a lot higher proportion of the population were killed. Okay, the genetic diversity doesn't really change too much. So it has to be very severe condition which can kill a lot of people. Otherwise, we cannot catch up based on the genetic data, we cannot see the change of the population size, because if it's just a portion of the population, the recovering is very fast, basically.
Okay, thanks.
Thanks.
Okay, very interesting. Albert Suleiman.
Okay, sorry, just a minute. I will open my camera. Gimana ini caranya? Lupa. Sorry if I cannot open my camera. I want us to Professor Lee. Professor Lee, you know, in the east coast of Sumatra and south coast of Kalimantan, there is many peatland area. It is in the peatland related to sea level rise, and it is possible to make a model how to peatland created. And I'm curious to what kind of mathematical model to explain the creation of peatland in east coast of Sumatra and south coast of Kalimantan. Thank you very much.
So you mean for the peatland, you want a model to simulate how they will grow in the future or reconstruct their history in the past?
Yeah, it's the history of peatland, how they created the peatland in this area.
Actually, we do have in our group have a new experts for peatland focused on the whole Southeast Asia region, including Borneo, and also for my model, we mainly focused on the sea level and also topography, the paleotopography and the bathymetry change. So I feel like this region, especially for example, for the east coast of the Sumatra, with the large area distribution of the peatland, that can have the high potential to resolve the previously I mentioned the treasure map of the high stand, because you have the sea level higher than present. When you drop, all this region, the peatland is flooded, and then they have the sea level, the past level record information. That's what we're trying to do, because we do have lots of the sea level reconstruction work along the Malay Peninsula, but we don't have any record. At least from my knowledge, I didn't see any publication in the Malacca Strait, in the southern Malacca Strait, I mean the east coast of the Sumatra. That's why I identified the locations. I only hope there are some more scientists who try to collect more data from there to reconstruct their history.
Yeah. We are welcome to collaboration. Okay.
Sure. We'll do in the future.
Yes. Thank you.
Thanks for your question.
All right. For the next question, Eddie Hermavan.
Yes, my name is Eddie. Can you hear my sound? Hello? Hello?
Yes, we can hear you.
Okay. First, thank you very much for me. My question will be addressed to Dr. Lee. Thank you very much for your nice presentation. I think this is the serious problem for Southeast Asia country. Several months ago, maybe last year, maybe you know, Jakarta is sinking. Southeast Asia is sinking. But I never heard Singapore is sinking. Is true or no? Because Singapore is also a small island, right?
Yeah.
Okay. It is maybe just my suggestions. Yeah. First, in your presentation, I show you focus on the sea level rise.
Yes.
Okay. But in my country, especially in northern part of Java Island or Jakarta, I said, not only sea level rise, because the impact of sea level rise is relatively very small, less than only a few millimeter, maybe 3 millimeter per year, or suggest wrong, But the other parameter have big, strong effect is land subsidence. So I suspect combination between sea level rise and land subsidence will be give more information. because two phenomena is very, very, what does I say? It's very, very big, give a strong impact. Not only cerebral rise, but lens subsidence can give more double or triple impact to the Jakarta thinking. So then I saw in your presentation using the Gaia model, is right?
Yes,
But
GIA
another
model.
model, Professor Tanggang from Malaysia suggested to use Cortex model. In general, NASA model. So we sometimes confused what kind model to use, Gaia model, NASA model, or Cortex model. So I think it's better to use all model than we use the ensemble model, the average model. Not like you mentioned, if strong or very strong emission, if a small emission, etc. Then etc. Then I think a combination between many model, many parameter, and making what is the best scenario means that if cerebral rise stable, but lens subsidence is not stable, or if lens subsidence stable, that cerebral rise is not stable. So many kind combination. Then we found the best model is when cerebral rise increase, when lens subsidence become decrease. So maybe this for me. It is very nice looking. Great job, great opportunity to study more, because this is the serious problem. So not only Singapore, but Southeast Asia. It is my suggestion one first. And the second one is we agree to use the mangrove. Yeah. But not only mangrove, maybe you can find another. Not like in Jakarta, we use the giant model. Giant wall. Not mangrove. This is the wrong decision, I think, I suspect. We are agreed to use the natural, like mangrove or another, So maybe my suggestion is how you can make the model. If with mangrove, how long, how far the cerebral rise can reach until the land. So we can make again and again. Model is the best choice, but please use another. Try another many kind model, not only NASA model and etc.
Maybe I can answer your first question first.
Okay.
And then first you mentioned which model should use. I guess there's no single model can solve all the problems. As I said, for the sea level change itself, because there are a variety of processes, the global, regional, and local. So for each model, they have their own capability. Like for the GIA, it's mainly the global scale or the regional scale, the process from the ice sheet melting and the land surface due to the loading and unloading of the large acid. So that's the background. And you said, emphasized a lot about the vertical motion, the subsidence. That's true for the, which will contribute to sea level rise much faster. That's why it happened in Jakarta. And the same for the IPCC projection. You will notice for the IPCC projection, they only provide the estimated vertical motion based on the tide gauge records. But the tide gauge records, they include information from the sea level change itself and also the vertical land motion. If you want to know the vertical land motion, you need to have the GPS. If you don't have, actually we did a study last year, just published in the Nature Sustainability about the sea level rise from land subsidence in major coastal cities, including Jakarta. So they use the INSA satellite image for like last 5 or 6 years. Then you, from the time series, you can know which area you subsiding or uplifting. But for inside itself, it's a problem. They only relative to their grid point. For each grid, they have a grid point or the motion, breaking motion relative to that one. If you cannot refer that one to the geoframe, then you don't know whether they are moving up, down, only floating right to this one. That's why I feel like you need to know the GPS, have at least one GPS in your study area, or you do campaign GPS annually, every year. You're right. For the sea level projection, you need to consider the local influence. That's why we can't apply the IPCC directly. Even in Singapore, we have their own projection program, including all the components of the sea level change I mentioned before. So do one by one and then integrate together.
Okay. And you apply your projection until 2100 for Singapore. But
yeah, we have to
less than 1 meter,
further.
yeah? Less than 1 meter. 0.92. It is true?
Yeah, that's for if you consider the high impact, low confidence, if the Antarctic, for the marine ice shelf instability and marine ice cliff instability they happen.
Direct to 2100, or you reduce, for example, every 10 year or every 5 year. So gradually you can say no.
Normally we use every 10 years for the projection.
Oh, okay. Okay, thank you very much for your answers again, and good luck for your great job. Good luck, Dr. Lee. Thank you very much, Dr. Gina. Thank you.
Yeah, you're welcome. You're welcome. Albert, I'm not sure if he still has his hand raised from before, or you have another question. If not, I have a question actually. So Tang Hua, very nice talk, beautiful graphics. I might want to ask you sometimes to steal some of those for lectures on sea level changes. I was wondering, so I've been working in Belitung Island a bit in Indonesia. And your colleague in Singapore, I don't know, Aaron Meltzner, he did some sea level reconstructions, but he found these very high amplitude, like maybe 1 meter changes over the time span of 150 years. Did you ever try, or that sort of like recreating that sort of high frequency signals, or is very difficult with the resolution that you have in your models?
Yeah, I guess for your point is about the Nature communication paper, the half-meter fluctuation.
Exactly.
Actually, we did try that because they found it's like a pretty large scale, both in the Belitung and also found the similar even in South China Sea. You see the signal, half-meter fluctuation in a very short time period. In the model, if we want to fix this, we must have ice either melt and then re-advance, which means you have to have a signal in the ice equivalent sea level change, the global mean sea level change. But that means they will happen elsewhere around the globe, maybe in North America even, but like in Caribbean or in Pacific Islands, they didn't say this. So we think it's maybe like more like a regional for different several processes, and then they sum up to make this, even the monsoon or the tectonics or the oscillation. For the GI, maybe a little bit, but it can't be purely due to that.
Because I'm very curious about this, like how this works. Like if, like you say, like if there is any sort of regional process with this loading, unloading of the Sunda shelf, that could cause this. So I was wondering, like your perspective on that. But
we tried, but we cannot make it a match for like half meter.
And do you reckon these sort of fluctuations mostly occurred around the peak of the mid-Holocene, or maybe also before and after?
I guess it should be, if it's before mid-Holocene, it will be more difficult to resolve because you have the melting water from the ice sheet. If it's after mid-Holocene, you can better refine to constrain because you don't have the much ice melting apart from maybe a little bit from Antarctic. Then for the regionally, you only have the ice load, the seawater loading, and also maybe if they do have the tectonics maybe, because all the Sumatra is pretty active, but I don't know the history, how active they are.
Okay, thanks a lot.
Thanks for
And then I have a question for Hilim. This is also, I mean, I guess a bit similar to what Danny was saying before. So, like I know, like in the Quaternary, there's been cycles with the sea level rising and falling, like roughly like every 100,000 years. So, as I understood, like the resolution of older data at this moment is not sufficient to say much about like changes in genetics around those periods.
I think I need to ask Dr. Kim. Hell, Kim. Sorry.
Yes.
Can you,
okay.
Sorry, Gino. Sorry. Dr. Kim, can you tell us what is the most dangerous city in the Southeast Asia that will be because of sea level rise until, I suspect not only Jakarta, I think. Another city, for example, maybe some part of small island in Philippines, or maybe it can also. What do you think about this?
You mean in future?
Yeah, in future, of course.
Well, I think you choose a different person to ask about that. Probably Tengua needs to answer the question. But before I pass to Tengua, I probably need to answer the Gino's question. So you mean the what's the period?
Yeah, so there was like I think like the Holocene sea level rise. There's also been a sea level rise, let's say around 130,000 years ago, and another one around 250,000 years ago. So yeah, so I would expect maybe like multiple of these. Like, yeah.
So, well, we didn't look at that period, but we also can. So this genome data actually can trace back up to like several million. But again, then it's not Homo sapiens anymore, right?
Yeah, sure.
So the people living here only from about 50 or 60,000 years ago.
Okay.
So that's why we cannot answer. It's not about the resolution of the genetics. It's more about which sample we can answer that question. Yeah.
You need more sample, yeah? Please come back.
Continue the.
Please come back again to Indonesia.
Oh yeah. I love to have an Indonesian sample, of course. We have some, but it's limited. So I love the Indonesian sample, of course. It's one of the most typical challenges for me. So Tengua, please.
As for Eddie mentioned about which is the most dangerous city, I feel like it's a very critical question.
It's a dangerous.
No, I mean it's going to be a sensitive. You can't claim which one. I mean, based on the subsidence, yes. Apart from Jakarta, Manila also suffered from the subsidence due to the groundwater extraction, and we also have a very low-lying areas. Similar for Singapore, because they have a very large area, the land reclamation, and so they are very high, very low elevation. They are all in the so-called low elevation coastal zones. That's why, like for Singapore government, they said they will like provide over $100 billion in the coming 10 years to deal with this level rise. Not only for the research, mainly for the coastal adaptation, for the engineering strategy, whether they should build the adjustable, the stay walls or something like that. So I guess every cities, if you are surrounded by the coastlines, you have the potential to be threatened by sea level rise or the coastal hazards. I guess that's the short answer. There's no answer for which one is the worst. If you don't do anything, you will be the worst, I guess.
I see. Okay. Thank you very much.
Thank you.
Okay. Thank you. Sorry. Okay.
So I think Padeni has another question.
Yeah. Thank you. Yeah, I think I would like to continue the question. I think from Henderson also is about the mass extinction of human. Well, I am interested in your turtle. I see on your graph that the turtle population decreased from LGM to, I don't see the scale, but I think from like the end of the Pleistocene.
All the way to present, yes.
All the way to present. I thought there's the late Pleistocene and then it increased again through the Holocene. That's what the turtle.
Let me show
Right.
you again, probably.
Yeah.
Then.
Anyway,
Anyway,
yeah,
but
okay. You could show me
well,
again.
but tell you the truth, all the population size decreased since the LGM and stay there very, very low. They are the endangered species.
Okay, so there is no change. Well, it's decreasing until now through the.
Yes.
Okay. Maybe I show you graph differently, but anyway, I'd like to ask what happened to human through from the LGM to Holocene, especially through the Younger Dryas, like in North America, for example. In Younger Dryas, the diversity, the DNA diversity in North America like decreased significantly in the Younger Dryas, but in other areas, I think there's no study yet to tell that. So there's a controversy whether.
Very happy you to ask
right.
about that, because we already submitted the paper.
So I really, so the big question is there like a mass extinction occurred to human in the Younger Dryas, because like the large animals in everywhere in the world, like mastodon or large animals extinct in late Pleistocene. So I would say that the Younger Dryas is very, very catastrophic to animals, but I think it's to human also. So that's why I'm asking about the size of the population after Younger Dryas compared to before. So could you really, like, from your available data, compare the population size from 13,000 to like 11,000?
You mean the particularly for Southeast Asian, or asking about the Native American? Or maybe everywhere.
It could be Sundaland or Singapore, Malaysia. Is there a decrease?
Well, the Sundaland one I already showed. So they decrease since continuously decrease during the deglaciation, including the Younger Dryas period. So I already kind of answered the previous question in that way. So it's part of the history. So we cannot distinguish if it's impact of the Younger Dryas or not. In terms of the other place, so because you mentioned the Native American, we also recently submitted the manuscript. We studied on this Native American, especially for South American. We also showed the decrease of the population size during the period, about the same period from the 10,000 years ago. But they massively decreased. But again, I cannot answer particularly about the Younger Dryas. It overlapped about that period, but it also overlapped other events like their migration. So
but at least your data showed that after the Younger Dryas, the population increased very significantly, right? Like 5 times or even 8 times. Is that correct?
In the Sundaland?
Yeah. And that drives the migration out of Sundaland because the population density increased significantly after the Younger Dryas.
Can you say exactly the period the Younger Dryas in?
The Younger Dryas is from 12,900 to 11,600 years ago.
Okay, so then it again overlap with this. But you're right. So it's increased. The population size is increased until about 8,000 years ago, and then dropped.
Okay,
so
that's very interesting.
Yeah, it's overlap with the sea level changes and the Younger Dryas as well. So I cannot say that which is the real impact, but it may overlap.
Thank you.
Okay, I don't know if there's still any other questions. Bu Yuda, do you have any questions?
No, I don't think so. You can continue. There is some comment in chat box. Maybe you can have, maybe Helen can have any comment from the chat box. Otherwise, then we will finish.
Yeah, I think we already talked about this out of Sunderland from the Danish question. So, but if you have any other opinion or anything else you want to discuss with me, please contact me. I'm happy to have a conversation.
Sure. Okay, then I think I mean it's been a good discussion already, and we've been busy for a while. So I think that's enough. So once again, thank you so much to our speaker Tanghwa and Helen. That was really interesting. I always admire it when people from like different fields manage to combine their expertise and come up with like really interesting study like this. So yeah, thanks once again for this very interesting. Yeah, this is a very interesting morning.
Thank you, Helen. Tanghwa.
Thank you so much having us.
Ya, terima kasih semuanya. Mungkin kita akhiri lecture hari ini. And thank you very much for Kim and also Tanghwa.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye.
Have a nice day.
I'm not sure if you see my response to the email. Oh, you also send me now.